talk about continuity, and that's just basically like when we're filling in the gap of the limit, and you'll see what I mean. Okay, so continuity is when you think about it, you think about like drawing the entire graph without lifting your pencil. So in other words, like without any breaks or jumps. Okay, and we state a function is continuous at point P. When we state that, we mean that the function passes through point P without a break. Okay, so let's now take a look at different forms of continuity or discontinuity. All right, so if we take a look at graph A, this graph, we can put our pencil down and we can trace it. Hold on. We can trace it without lifting our pencil. Beautiful, it's continuous. Okay, B, this is point discontinuity because we'd have to pick up our pencil because there's a hole, and then we'd have to put our pencil back down and continuously draw our line. Okay, so there's a discontinuity here at x equals 1, and this is a point discontinuity. Okay, C, this is a jump discontinuity. So again, just to recap, when we read a graph, we read it like a book. You start on the very left-hand side and you go to the right. So we start here, we come up here, and then we have to jump, we have to pick up our pencil, and then we complete the graph. So there's a jump discontinuity at, again, x equals 1. And finally, another type of discontinuity is an asymptote. So we start at the left-hand side, we go all the way up. Eventually, we have to pick up our pencil and draw the other part of the graph. Okay, and this is called infinite discontinuity. Okay, so in order to be continuous, this is what I mean by we're filling in like the part that's missing from the puzzle of like limits. So we know that the limit as x approaches a from the left and the limit as x approaches a from the right. If those two approach the same number, we know that the limit exists. But now what we're doing is we're actually filling in that this point here in the middle has to actually be the same number. So if we sub in f at a, like right at a, it has to be the same number. Okay? Otherwise, it's discontinuous. So you might be saying, well, it has to be the same number. Well, not necessarily, because you could have like this. It could be defined up there and then continue. Right? So this would be like just a complete disconnect just for that one. So the limit would exist for this function here, like let's just call it f at x, but it would be discontinuous because there would be like that jump. Okay, so let's try example 1. So let's actually graph the following function. Okay, so it's a parabola of x squared minus 3 when x is less than or equal to negative 1. So again, like I was showing you before, I would take that and I would put negative 1 squared minus 3. So 1 minus 3, negative 2. So including, this is important, including that negative 1, we're going to plot it at negative 2. And it's going to be a parabola, and it's going to open up because it's positive. Now, x minus 1 is a line. So when x is greater than negative 1, so let's actually sub that in. Negative 1 minus 1 is negative 2. We start at negative 2 again. Positive slope, positive 1. This is negative 1. It's going to be the y-intercept. Okay? So this is going to be the x minus 1. This is going to be the x squared minus 3. That's a parabola, that's a line. They both meet at the same point. So that's the graph. Now determine if the limit as x approaches negative 1 of f at x. Determine the limit. So the limit equals negative 2. Determine f at negative 1. So we did that. We have to consider this one right here because it includes negative 1. That's also negative 2. So therefore, is f continuous at x equal negative 1? Explain. Yes, it is continuous. And the way you have to explain is the limit as x approaches 1 from the negative side equals negative 2, and that equals the limit as x approaches 1 from the positive side of f at x. And that's it. So you showed how, get a color. As we come in from the negative side, we approach negative 2. as we come in from the positive side, we approach -2. And at that number, we subbed it in, and we got -2. Therefore, it's continuous. Okay, example 2. We're going to test the continuity of each of the following. We might have to do this in one more video. And x equals 2. If it's not continuous, then we're going to give you a reason why. So we're going to talk about whether it's an asymptote or a point discontinuity or a jump discontinuity. Okay, so let's take A. A is just simply a polynomial, degree 3. Okay, so in my head, I already know that that's continuous, but let's actually prove it. Okay, so the limit as x approaches 2 of x cubed minus x, we know that we can do 2 cubed minus 2, which is 8 minus 2, which is 6. And we know that f at 2, which is basically what we just did, is 6. Therefore, it's continuous. Okay, also we know it's a polynomial. Okay, let's try B. Okay, let's go. The limit as x approaches 2 of x squared minus 2, x minus 2 over x minus 2. Okay, immediately this is a flag. X minus 2, if we sub in the 2, we are going to get 2 minus 2, which is 0. If we do a straight substitution, 4 minus 2 minus 2, we get 0 over 0. We can't do that. So let's factor the top. See what we get. So I get, what two numbers, I don't know where I put a line there. What two numbers multiply to -2 and add to -1? X minus 2, x plus 1. So we can cancel those out. Therefore, the limit as x approaches 2 of x plus 1 is just 2 plus 1, which is 3. Now, let's actually, I was going to say let's actually plug in, well, it's not f, it's g. G at 2, but it's 0 over 0, right? We already did that. So therefore, discontinuous. Discontinuous, U-O-U-S, at x equals 2, and this is a vertical discontinuity, sorry, vertical asymptote, so vertical asymptote. All right, so let's do the next one. Let's do C. So they're saying this is a piecewise function. It's written a little bit differently. They're giving us the exact same formula as in B, but what they're saying is when h is 2, so they're subbing it in for us, it equals 3. So we knew that the limit, let's go, the limit as x approaches 2 in this case, and let's call this h at x, we know from example B or question B that it equals 3. Now, h at 2 also equals 3. So they gave us that component. They said h at 2 equals 3. Therefore, we can say that the limit as x approaches 2 from the negative side equals 3. And that's the same as when x approaches 3 from the positive side. Oops. H of x. So therefore, it's continuous.